88% of scientists agree. We are not alone in the universe. In a recent survey published in Nature Astronomy, over 1,000 scientists from various fields reached a striking consensus. Extraterrestrial life almost certainly exists somewhere among the billions of habitable worlds in our cosmos. What if we're already detecting their footprints in the cosmic forest? Most surveyed experts, 67%, believe intelligent life exists beyond Earth. The real mystery lies in whether advanced civilizations have mastered gravity manipulation, technology we might be glimpsing through gravitational wave observations. Today, we'll explore how cutting-edge quantum physics experiments could offer our first window into something extraordinary happening in the stars. The scientific consensus on extraterrestrial life. When you ask an astrobiologist about the likelihood of extraterrestrial life, don't expect hesitation. A recent survey published in Nature Astronomy revealed something remarkable. 86% of researchers in this field believe we're not alone in the universe. This wasn't just a casual poll. It was a methodical scientific survey with rigorous standards, reaching across disciplines and international boundaries to capture the most comprehensive picture of scientific opinion on this question to date. The survey gathered responses from researchers across 30 countries, ensuring a globally representative sample of scientific thought. What makes this particularly compelling is the participant profile. Established scientists with published work in astrobiology and related fields. The methodology specifically targeted researchers who had contributed peer-reviewed publications on topics related to the origin and distribution of life in the universe, giving us insight into what the actual experts believe. This overwhelming consensus exists despite an apparent contradiction. We haven't discovered a single confirmed example of life beyond Earth. Not a microbe on Mars, not a mysterious signal from distant stars, nothing definitively biological. Yet the scientific confidence remains remarkably high. To understand this seeming paradox, we need to examine the statistical reasoning that drives scientific thinking on this question. The universe contains approximately 100 billion galaxies, each hosting an average of 100 billion stars. Around these stars orbit countless planets. Current estimates suggest there may be more planets than stars in our galaxy alone. The Kepler mission and subsequent observations have revealed that potentially habitable planets are abundant. Conservative estimates suggest at least 300 million potentially habitable worlds exist just within our Milky Way galaxy. When multiplied across the observable universe, the numbers become almost incomprehensible. This creates what scientists refer to as a probability volume, a vast mathematical space of possibilities where even extremely rare events become virtually inevitable. It's like a cosmic lottery with billions of tickets in play. The odds of any single ticket winning might be minuscule, but with enough tickets, winners emerge somewhere. The consensus isn't based on wishful thinking or science fiction. It's a calculated assessment of cosmic real estate and the chemistry of life as we understand it. The survey reveals important nuances in scientific thinking. While 88.4% of researchers agree that microbial extraterrestrial life exists, the confidence drops to 67.4% when considering intelligent life. This distinction reflects our understanding of evolutionary history on Earth. Simple life appeared relatively quickly after the planet cooled, while complex multicellular organisms took billions of years more to develop, and intelligence capable of technology is more recent still. Perhaps more telling than a high agreement rate is the remarkably low disagreement rate. Only 10.2% of surveyed scientists explicitly disagreed with the existence of extraterrestrial life. This distribution of opinions reveals something crucial. There's very little active opposition to the idea that life exists beyond Earth. When removing neutral votes and focusing solely on researchers who took a definitive position, the agreement rate climbs to 97.8%. What drives this confidence? Beyond sheer statistical probability, scientists point to several lines of evidence. The building blocks of life, organic molecules like amino acids, have been detected throughout space, from interstellar clouds to comets within our solar system. Water, considered essential for life as we know it, appears to be abundant throughout the cosmos. The fundamental chemical ingredients for biology seem universally distributed across the vast canvas of our universe. Additionally, life on Earth has demonstrated remarkable adaptability, thriving in environments once thought completely hostile to biology. We've discovered organisms living in boiling hot springs, deep-sea thermal vents, highly acidic environments, and even the radiation-filled environment outside the International Space Station. This adaptability suggests that life might emerge and persist in a wider range of conditions than previously thought possible. The scientific community also points to the rapid emergence of life on Earth as evidence for its potential commonality. The geological record suggests that basic life forms appeared almost as soon as the planet's surface cooled enough to permit liquid water within the first few 100 million years of Earth's 4.5 billion year history. This rapid development implies that the emergence of simple life might be a relatively straightforward consequence of planetary chemistry under the right conditions. These lines of evidence, combined with the limitless cosmic possibilities, create a compelling scientific case for extraterrestrial life. The consensus expresses a well-reasoned confidence based on our best understanding of biology, chemistry, and astronomy. If simple life forms exist elsewhere, the next question becomes far more intriguing. Have any evolved into technologically advanced civilizations? And if so, how might we detect them? Traditional SETI efforts have focused primarily on radio signals, but these methods have significant limitations. Radio transmissions weaken with distance according to the inverse square law, making detection across interstellar distances challenging unless the signal is specifically directed toward us. This is where gravitational signatures enter the picture. Any sufficiently advanced civilization would likely manipulate energy and matter on scales large enough to create detectable gravitational effects. Unlike electromagnetic signals, gravitational patterns don't degrade in the same way over vast distances. They propagate through the universe relatively unchanged, potentially providing evidence of engineering projects that conventional detection methods might miss. Consider what an advanced civilization might construct. Massive orbital habitats, stellar engines that extract energy from stars, or technologies that manipulate the fabric of space-time itself. Each would create distinctive gravitational patterns, anomalies that couldn't be explained by natural processes alone. As our gravitational wave detectors grow more sensitive, we're developing the capacity to identify these potential signatures of intelligence. This approach transforms how we search for extraterrestrial civilizations. Rather than waiting for them to deliberately contact us, we can look for the gravitational footprints their existence would inevitably leave on the cosmos. It's like walking through a forest. You might not see the animals themselves, but footprints, disturbed vegetation, and other signs reveal their presence. The universe may contain similar traces of intelligence that we're only now learning to recognize. Gravity's quantum frontier, the UC Berkeley experiment. Those cosmic footprints might be more elusive than we thought, requiring us to look at both massive gravitational waves and quantum-level gravitational interactions. At this very moment, researchers at UC Berkeley are suspending atoms between reality states to detect forces so subtle they might reveal whether gravity itself contains hidden dimensions an advanced civilization could potentially navigate. The Berkeley experiment represents a quantum leap in how we search for gravitational anomalies. The research team, led by physicist Holger Muller, has developed an atom interferometer that operates on principles fundamentally different from conventional gravity detectors. Rather than measuring the displacement of macroscopic objects, their apparatus exploits the wave-like nature of matter at quantum scales. We've created what amounts to a quantum ruler for gravity, explains Muller. By placing cesium atoms in spatial superposition, we can measure gravitational fields with unprecedented precision. This quantum ruler works by etching measurements onto the fabric of reality itself. The experimental setup is elegant in concept, but extraordinarily complex in execution. Cesium atoms are cooled to near absolute zero using laser techniques. slowing their motion to a virtual standstill. These ultra-cold atoms are then placed in a state of quantum superposition using carefully calibrated laser pulses. The Berkeley team has extended superposition time to several seconds, allowing the atoms to act as exquisitely sensitive gravitational probes. When an atom exists in superposition, it occupies multiple positions simultaneously, with each position experiencing the local gravitational field slightly differently. As the atom evolves through time, these different gravitational experiences create a measurable phase difference between the components of the atomic wave function. This approach detects forces up to 5 times more precisely than previous methods. The team incorporates optical lattices, essentially grids of light created by intersecting laser beams that hold atoms in place while maintaining their quantum properties. These optical lattices function as quantum test tubes, isolating the cesium atoms from environmental disturbances. When a superposition state collapses through measurement, the phase difference between the two halves of the atomic wave function reveals minute variations in the gravitational field. What we're looking for are deviations from what Einstein's theory of general relativity predicts, notes one of the team members. If we find such deviations, it could point to new physics beyond our current understanding, possibly a fifth fundamental force. This fifth force would join gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. 2 particular candidates are theoretical particles known as chameleons and symmetrons. These hypothetical particles would mediate a force that changes strength depending on the local environment, becoming stronger in vacuum but weaker in dense matter. This variable strength explains why such particles might have evaded detection in Earth-based laboratories. The connection to dark energy makes this search particularly significant. Many theoretical physicists suspect that chameleon or symmetron particles might be responsible for dark energy's cosmic expansion effects. If confirmed, such particles would solve one of the greatest puzzles facing modern science. As we push these measurements to their limits, Muller observes, we're essentially developing sensors that could detect the fingerprints of advanced technology manipulating the fabric of space-time itself. From an astrobiological perspective, the implications are profound. If a fifth force exists and operates differently from our known forces, it could potentially be manipulated by a technologically advanced species. A civilization that could control such a force might alter the effective mass of objects or create localized regions where gravity behaves differently. They might generate gravitational shields or construct propulsion systems that exploit these particles' unique properties. The energy requirements would be enormous by our standards, but not necessarily prohibitive for a civilization thousands or millions of years more advanced than our own. The detection capabilities developed at Berkeley might someday allow us to identify the gravitational signatures of such technologies. Advanced civilizations manipulating the fifth force would create distinctive patterns in the gravitational field, patterns that might appear as anomalies when viewed through conventional physics. What we're developing here is essentially a new kind of telescope, explains Muller. But instead of looking for light, we're searching for subtle distortions in the gravitational field that might indicate natural or unnatural phenomena. The Berkeley apparatus can detect spatial and temporal variations in the gravitational field, potentially revealing dynamic manipulation rather than just static anomalies. This distinction is crucial, as technological manipulation would likely produce distinctive patterns of variation over time. While the experiment hasn't yet detected definitive evidence of a fifth force, it has established the most stringent constraints to date on theories proposing chameleon particles. These constraints help physicists refine their models and narrow search parameters for future experiments. For SETI, these developments represent a paradigm shift. Traditional efforts have focused primarily on electromagnetic signals, deliberate transmissions, or technological leakage. Gravitational SETI opens an entirely new channel, focusing on the fundamental manipulation of space-time itself. An advanced civilization might prefer gravitational engineering over electromagnetic communication for several reasons. gravitational signals propagate unimpeded through dust, gas, and other matter that might block electromagnetic transmissions. They carry information across cosmic distances without degradation. And perhaps most importantly, the ability to manipulate gravity at quantum scales would represent a technological achievement far beyond mere radio communication, a true marker of an advanced civilization. How are scientists using atom interferometers to search for a fifth fundamental force? By creating quantum superpositions that can detect minuscule gravitational deviations impossible to measure with conventional technology. These experiments push the boundaries of quantum physics and gravitational theory simultaneously, opening windows into phenomena that might otherwise remain invisible. Anomalous gravity, wide binary stars breaking physics. Beyond the controlled environment of Berkeley's laboratories lies an astronomical mystery that has physicists questioning the very foundations of gravity. When wide binary stars separated by thousands of astronomical units were measured by the Gaia Space Telescope, their orbits revealed something impossible. There, accelerating 40 to 50% faster than Newton's laws allow. An international team of astronomers published their findings in the Astrophysical Journal after analyzing data from the European Space Agency's Gaia mission, which has been mapping the positions and movements of billions of stars with unprecedented precision. The researchers specifically targeted wide binary star systems, pairs of stars orbiting each other at extreme distances, to test how gravity behaves at very low accelerations. What makes these findings so remarkable is the systematic nature of the deviation. These stars perform a cosmic dance that defies our fundamental understanding of physics, consistently violating Newton's laws of motion in identical ways across different star systems throughout our galaxy. The anomaly appears specifically when two conditions are met. The stars must be separated by more than 2,000 astronomical units. That's 2,000 times the distance from Earth to the Sun, and the acceleration between them must fall below 1 nanometer per second squared, an incredibly small force equivalent to the gravitational pull exerted by a grain of sand at a distance of 1 kilometer. The research team went to extraordinary lengths to ensure their findings weren't contaminated by observational errors or other celestial influences. They meticulously selected pure binary systems that weren't interacting with other stars or massive objects, eliminating potential third bodies that might disrupt the orbital mechanics. They also accounted for the galactic background, ensuring the anomalous acceleration wasn't simply the result of the Milky Way's overall gravitational field. What's particularly compelling is that a second independent research group, using entirely different selection criteria and analytical methods, reached the same conclusion. This team focused on different binary star pairs but observed the identical acceleration boost at the same threshold of separation and acceleration. When two teams using different approaches arrive at the same anomalous result, scientists take notice. The acceleration threshold, where this anomaly appears, 1 nanometer per second squared, carries special significance in gravitational physics. This value happens to be remarkably close to a number known as A, pronounced a naught, which represents the critical acceleration value in modified Newtonian dynamics, MOND, a theoretical framework proposed as an alternative to dark matter. The fact that wide binary stars begin misbehaving precisely at this threshold has profound implications for our understanding of gravity. The researchers took extraordinary precautions to eliminate observational biases. For instance, they carefully accounted for projection effects. Since we observe these systems from Earth, we're not always seeing their true separation, but rather their apparent separation projected onto our line of sight. Through statistical methods and three-dimensional motion analysis, they confirmed the anomaly persists even after correcting for these effects. Most intriguing is how cleanly the data demonstrates the transition from Newtonian physics to something else. These binary stars move in a well-choreographed pattern until they reach a specific distance from each other. Then suddenly, their dance changes tempo. As they move further apart and experience weaker gravitational attraction, there's a clear trigger point where they begin accelerating faster than they should. This clean transition suggests we're witnessing a fundamental property of gravity rather than some random influence. The implications extend far beyond these specific star systems. If gravity itself behaves differently at extremely low accelerations, this could help explain other cosmic mysteries without invoking dark matter. The invisible substance thought to comprise 85% of the universe's mass. Some theorists suggest these binary star anomalies might be the most direct evidence yet from modified gravity theories. But there's another, more provocative possibility. The precise, consistent nature of the acceleration boost, always activating at the same threshold, bears the hallmarks of a calibrated effect rather than a messy natural phenomenon. These gravitational anomalies display a curious degree of precision that has some researchers quietly questioning whether we might be observing the fingerprints of advanced technological intervention. The consistency across different binary systems is particularly striking. Natural phenomena typically show variations based on the specific conditions of each system, differences in stellar mass, composition, age, and environment. Yet these acceleration anomalies appear remarkably uniform, as if adhering to a single underlying principle or design. Some astronomers have noted that wide binary star systems would make ideal targets for advanced civilizations seeking to establish habitable environments far from the intense radiation of their host stars. The stable, predictable orbits of these systems, combined with the vast available space, could provide perfect conditions for engineered habitats or energy collection systems. If a civilization possessed the ability to manipulate gravitational fields, these binary systems might serve as ideal frameworks for massive engineering projects. The technology required to create such effects would be far beyond our current capabilities, but not necessarily beyond the realm of theoretical physics. Manipulating space-time to alter gravitational effects is consistent with Einstein's general relativity, which describes gravity as the curvature of space-time itself. Of course, the scientific community remains appropriately cautious. The primary explanation focuses on natural physical processes rather than speculative technological interventions. Most researchers are exploring whether these anomalies might be explained by modifications to our understanding of gravity or by previously unaccounted natural phenomena. Further observations will be crucial. The next generation of space telescopes and gravitational wave detectors might provide the precision needed to determine whether these anomalies follow patterns consistent with natural physical laws or display characteristics that might suggest artificial origins. Modified Newtonian dynamics versus alien engineering. What separates a natural law of physics from an engineered system when observed from a distance? As we examine these binary star anomalies, we face a profound scientific crossroads. Either we must modify our fundamental understanding of physics or consider the possibility that something or someone might be modifying gravity itself. The leading natural explanation for these acceleration anomalies is modified Newtonian dynamics, or MOND. First proposed by Israeli physicist Mordechai Milgram in 1983. MOND suggests that Newton's laws of motion need adjustment at extremely low accelerations. When acceleration falls below a critical threshold, approximately 1/10,000,000th of Earth's surface gravity, denoted as A, the relationship between force and acceleration changes. The acceleration becomes proportional to the square root of the force rather than directly proportional as in Newton's second law. What makes the binary star observations compelling is that they show gravitational anomalies appearing precisely at this theoretical threshold. When stars experience accelerations below A, their orbital velocities exceed Newton's predictions by that consistent 40 to 50% factor, exactly matching MOND calculations. MOND was originally proposed to address galaxy rotation curves, stars orbiting galactic centers faster than they should based on visible matter. While scientific consensus attributes this to dark matter, MOND suggests gravity itself behaves differently at extremely low accelerations, eliminating the need for dark matter entirely. MOND successfully predicts gravitational behavior across vastly different scales, from binary stars separated by thousands of astronomical units to galaxies spanning hundreds of thousands of light years. This consistency across scale resembles how natural physical laws operate, much like how a natural waterfall follows the same gravitational principles whether it's a small stream or Victoria Falls. However, MOND struggles with certain observations, particularly galaxy clusters, where it still requires additional unseen mass. It also lacks a comprehensive relativistic framework that would unite it with our understanding of cosmic expansion and black holes. These theoretical gaps leave room for alternative explanations, which brings us to the technological hypothesis. What if these gravitational anomalies represent not a new law of physics, but evidence of technological intervention? Advanced civilizations might manipulate gravitational fields for creating artificial habitats, enabling interstellar propulsion, or harvesting energy from binary star systems. Consider the difference between a natural phenomenon and engineered technology. A natural geyser erupts based on consistent geological principles, while a fountain operates on engineered parameters for specific purposes. Similarly, natural gravitational fields follow universal mathematical rules, while engineered fields might show optimization patterns. The technological explanation becomes plausible when we consider potential mechanisms. One approach would involve warping space-time using concentrated energy densities, similar to Miguel Alcubierre's faster-than-light drive concept. The Alcubierre drive would contract space-time ahead and expand it behind, creating a wave that carries a ship within normal space. While beyond our capabilities, quantum gravity effects could drastically reduce energy requirements. Another approach might use the same chameleon particles being sought in quantum gravity experiments. These particles could mediate a force that varies with environmental conditions. Advanced civilizations might control these particles to create gravitational shields or amplifiers, producing the observed acceleration modifications. To distinguish between natural MOND and technological engineering, we need to examine patterns. Natural physical laws produce uniform effects without preference for specific configurations. Technological interventions would likely display patterns optimized for specific purposes, stability, efficiency, or functionality. If gravitational anomalies appear stronger around stars with particular spectral characteristics suitable for life, this suggests purposeful selection rather than a universal law. Similarly, variations related to galactic position might indicate network-like structures rather than a fundamental constant. Timing patterns would be revealing. Natural laws operate continuously across cosmic timescales. If the acceleration effect fluctuates over time or displays periodicity, this could indicate active control rather than a passive physical law. Geometric signatures offer another test. Natural gravitational fields follow smooth distributions based on mass. Engineered fields might show complex geometries optimized for specific purposes, perhaps creating stable regions where gravitational potential remains constant despite orbital variations. We could also examine gravitational polarization effects. While natural gravity acts uniformly in all directions, engineered technology might create asymmetric fields with directional preferences, detectable through mapping acceleration vectors around anomalous systems. Princeton University researchers have proposed specific tests to differentiate between these explanations, including measuring anomalous acceleration vectors across multiple binary systems and comparing them against computer models of both MOND and various engineered configurations. The Japan Aerospace Exploration Agency has proposed sending specialized probes to the outer solar system, where solar gravity reaches the critical acceleration threshold. These probes would determine whether objects experience the same acceleration boost seen in binary stars when entering this regime. If these tests reveal inconsistencies, if the effect appears stronger in some regions than others, or shows patterns correlating with factors irrelevant to gravity, we might have evidence of large-scale engineering by advanced civilizations. The 40 to 50% acceleration boost appears with such mathematical precision that it raises a possibility. Have we discovered the operational parameters of gravitational technology rather than a new law of nature? The specific threshold value might represent an optimization point where energy efficiency and gravitational modification reach ideal balance, echoes of cosmic engineering. Gravitational waves leave behind something curious after they pass, a subtle distortion in space-time that physicists call gravitational wave memory. Unlike the waves themselves, which oscillate and fade, these memory effects create permanent displacements in the fabric of reality. While Einstein's equations predict such phenomena, recent analyses of LIGO and Virgo detector data have revealed something unexpected: secondary signals that arrive after the main gravitational wave event. These secondary signals, or echoes, present us with a fascinating scientific puzzle. According to classical general relativity, black holes should absorb all incoming radiation without reflection, like perfect cosmic sponges. When gravitational waves emanate from black hole mergers, they should produce clean, singular signals without any subsequent reverberations. Yet detector data suggests otherwise. Several research teams, including groups at the Perimeter Institute and the University of Waterloo, have identified patterns consistent with gravitational wave echoes in multiple black hole merger events. These echoes appear as time-delayed repetitions of the original signal, gradually diminishing in strength with each recurrence, similar to how sound echoes bounce off canyon walls before fading away. What makes these echoes particularly intriguing is their direct challenge to our understanding of black hole physics. Under classical general relativity, the event horizon represents a point of no return. Nothing, not even gravitational waves, should reflect back once crossing this boundary. The presence of echoes suggests something exists near black holes that causes gravitational waves to partially reflect. Quantum gravity theories offer one potential explanation. At quantum scales, the sharp boundary of a black hole's event horizon might be replaced by a quantum structure with reflective properties. These quantum surfaces would exist just outside the event horizon, creating what physicists call a gravitational mirror, capable of reflecting a portion of the gravitational wave energy back outward. Like the lingering notes of a cosmic symphony, these echoes resonate through space-time with distinctive timing signatures. The delay between initial signal and first echo corresponds to light's travel time from the event horizon to the reflective surface and back, typically appearing milliseconds after the main merger signal. Gravitational wave detectors like LIGO, Virgo, and CAGRA capture these echoes through precise measurements of laser beam interference patterns. As gravitational waves pass through Earth, they momentarily stretch and compress space-time, causing minute changes in the path length of laser beams. The echoes create secondary interference patterns with distinctive features that distinguish them from detector noise. Two competing models explain the reflective mechanism behind these echoes. Boltzmann reflectivity proposes that quantum effects create a semi-transparent membrane near the event horizon that partially reflects gravitational waves. Alternatively, exotic compact objects, ECOs, theory suggests alternatives to traditional black holes with hard surfaces or shells where event horizons would normally be, naturally reflecting gravitational waves. What makes these echo patterns potentially relevant to the search for advanced civilizations is their possible artificial origin. If a sufficiently advanced civilization were to construct megastructures near black holes, perhaps to harvest energy or create computational substrates, these structures would necessarily interact with passing gravitational waves, creating reflection patterns indistinguishable from natural quantum echoes. The energy and momentum flux patterns within these echoes could reveal whether they originate from natural quantum surfaces or engineered structures. Natural reflections would likely produce uniform, omnidirectional echo patterns governed by the underlying physics. In contrast, engineered structures might create asymmetric reflection patterns optimized for specific purposes. Physicist Vitor Cardoso and his team at the University of Lisbon have developed mathematical models to distinguish between different types of echo signatures. Their work suggests that the polarization properties of gravitational wave echoes could reveal whether their source is uniform and natural or structured and artificial. Several observed characteristics of gravitational wave echoes raise intriguing possibilities about their origin. The reflection efficiency appears unusually high in some detected echoes, higher than most quantum gravity theories predict. Certain echoes show frequency-dependent reflection patterns that align more closely with engineered resonance structures. Some echoes exhibit time domain features suggesting active rather than passive reflection mechanisms. The positioning of potential. Reflective structures near black holes would be strategically significant for advanced civilizations. Black holes represent the universe's ultimate energy sources, concentrated masses capable of converting matter to energy with perfect efficiency. A civilization capable of manipulating space-time might position structures near black hole horizons to harvest this energy while using the extreme gravitational environment for computational advantages. Theoretical physicist Avi Loeb of Harvard University has proposed that the optimal position for energy extraction and computational infrastructure would be approximately 1.5 times the Schwarzschild radius from a black hole center. Coincidentally, the same region where gravitational wave echoes appear to originate, according to current analyses. The LIGO-Virgo collaboration continues to refine their search for echo signatures, with planned sensitivity upgrades potentially capable of resolving the fine structure of these phenomena. The next generation of gravitational wave observatories, including the space-based LISA mission and the proposed Einstein telescope, will provide unprecedented detail about gravitational wave echoes, potentially revealing their true nature. If future observations confirm patterns consistent with engineered structures rather than natural quantum surfaces, the implications would be profound. We might be observing the technological fingerprints of intelligences capable of manipulating the fundamental structure of space-time itself. The search for gravitational wave echoes represents a convergence of our most advanced theoretical physics with our search for cosmic companions. While conventional SETI focuses on electromagnetic signals, gravitational wave archaeology opens a new frontier: the possibility of detecting intelligences through their manipulation of gravity itself. Beyond Kardashev, Stellavores civilizations. Beyond manipulating gravity, truly advanced intelligences might have abandoned conventional energy harvesting altogether. The Kardashev scale has shaped our thinking for decades. But what if the most powerful civilizations in the cosmos aren't building Dyson spheres around stars, but literally feeding on them? The Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964, categorizes civilizations based on their energy consumption. A Type 1 civilization harnesses the total energy available on its planet, about 10 to the power of 16 watts for Earth. A Type 2 masters the entire output of its star, capturing approximately 10 to the power of 26 watts from a sun-like star. And a Type 3 civilization controls the energy of its entire galaxy, accessing around 10 to the power of 36 watts. For decades, SETI researchers have focused on finding Type 2 civilizations by searching for Dyson spheres, hypothetical megastructures that completely encompass stars to capture their energy output. These would appear as infrared bright, but optically dim objects in our telescopes. But this framework makes a critical assumption, that advanced civilizations would prioritize capturing a star's electromagnetic radiation rather than its mass. The concept of Stellavores, literally star eaters, represents a paradigm shift in how we conceptualize technological advancement. Instead of building structures around stars to capture their radiated energy, these hypothetical civilizations would directly consume stellar matter through mass energy conversion. Consider a star like a cosmic feast. While Dyson sphere builders merely collect the heat radiating from the oven, Stellavores would devour the entire meal, extracting every calorie of potential energy from the star's substance itself. Our sun converts only about 0.7% of its mass into energy through nuclear fusion. However, direct mass energy conversion could theoretically convert 100% of mass into usable energy, following Einstein's famous E equals mc squared equation, a 143-fold increase in available energy from the same stellar resource. If a civilization were to consume just 1% of our sun's mass through direct conversion, They would access more energy than the sun will radiate throughout its entire 10 billion year lifetime. This approach to energy acquisition would place Stellavores beyond the conventional Kardashev scale entirely. The Stellavore hypothesis aligns with technological development patterns. Energy efficiency increases over time. Just as human technology has progressed from wood burning to nuclear fission, releasing increasingly more energy from the same amount of matter, advanced civilizations would eventually prioritize matter consumption over radiation harvesting. This reframes our understanding of advanced civilizations. Rather than expanding outward to capture energy from multiple stars, Stellavores might focus intensely on exploiting single stellar systems to their fullest potential. This intensive rather than extensive development pathway suggests that advanced civilizations might remain more localized than we previously imagined. What might we observe if a star were being consumed? Imagine watching a celestial vampire feeding on a star. We might detect unexpected dimming patterns distinct from natural processes or orbiting planets. The star spectrum could show evidence of artificially accelerated mass loss or unusual element distribution inconsistent with stellar evolution models. The gravitational consequences would be particularly telling. Stars undergoing artificial mass reduction would display altered orbital dynamics in multiple star systems. Their gravitational influence on surrounding bodies would decrease in ways that wouldn't align with natural stellar evolution timelines. Particularly intriguing evidence might appear as unexpected energy signatures. Mass energy conversion on such a scale would likely produce detectable waste heat, gravitational perturbations, or high-energy particle emissions with non-natural frequency distributions, fundamentally different from those produced by standard fusion processes. The power requirements for directly manipulating stellar mass are immense, but not insurmountable for civilizations that have mastered gravitational engineering. By creating precisely controlled gravitational fields, an advanced civilization could essentially siphon plasma from a star's outer layers without destabilizing it completely. This process would require precise manipulation of space-time, exactly the kind of engineering that might produce gravitational wave echoes. Binary star systems offer particularly attractive targets. In these systems, two stars orbit each other, sometimes exchanging material through natural processes. An accreting binary, where one star pulls material from its companion, provides a natural stellar mass transfer mechanism that could be technologically enhanced. Different stars might serve different purposes for Stellavores. Main sequence stars like our Sun offer stability, while massive stars provide more material but burn out quickly. Red giants, with their expanded, loosely bound outer layers, might represent ideal feeding grounds due to the relative ease of extracting their matter. The implications for our search strategies are profound. Traditional SETI has focused on communication signals or waste heat from Dyson spheres. If Stellavores exist, we should instead look for unexplained mass loss rates, unusual composition changes, or gravitational anomalies suggesting active extraction. Accreting binary systems already transfer mass naturally, making them perfect camouflage for artificial intervention. A civilization could enhance the natural accretion process, hiding their activities within what appears to be a natural phenomenon. The key to detection would be identifying statistical outliers, binary systems with mass transfer rates, directions, or efficiencies that deviate from astrophysical models. This connects directly to the gravitational anomalies observed in wide binary stars. The consistent 40 to 50% acceleration boost at specific distances might not be a natural constant, but a technological signature, perhaps the optimal efficiency range for stellar mass extraction technology. The Stellavore concept helps explain the missing Type 3 civilizations. If the most efficient path is intensive exploitation of individual stellar systems rather than extensive expansion, we wouldn't necessarily see galaxy-wide engineering projects. Instead, we might find isolated instances of stellar engineering that could be easily overlooked or misclassified as natural phenomena, representing a fundamental shift in how we conceptualize cosmic evolution. Accreting binaries, prime SETI targets. If advanced civilizations are harvesting stellar matter, they wouldn't start by engineering complex extraction mechanisms. They'd look for systems where nature has already done the heavy lifting. Accreting binary stars, with their continuous streams of transferring material, represent cosmic conveyor belts of ready-to-harvest energy. Unlike isolated stars, accreting binaries feature two stars in close proximity where one star actively pulls material from its companion. These systems come in various configurations, but the most common involve a main sequence or giant star orbiting alongside a compact object like a white dwarf, neutron star, or black hole. The compact object's powerful gravitational pull creates an accretion disk, a flattened ring of superheated gas spiraling inward from the donor star. The physics of these systems makes them particularly attractive for potential advanced civilizations. In a typical accreting binary, material flows through the inner Lagrangian point, the gravitational balance point between the stars, forming a predictable stream that feeds the accretion disk. This natural mass transfer process delivers pre-extracted stellar material without requiring the enormous energy investment of removing mass from a single star's gravitational well. What makes these systems especially valuable is their longevity. Many accreting binaries can sustain mass transfer for millions or even billions of years, providing a stable, long-term energy resource. The donor star functions as a massive reservoir, while the compact object serves as the energy extraction mechanism, with the accretion disk acting as a processing center where matter is heated to millions of degrees. From an observational standpoint, we understand the baseline characteristics of these systems well. Accreting binaries produce distinctive light curves with predictable patterns of brightening and dimming as the stars orbit each other. The accretion disks emit radiation across multiple wavelengths, with spectral signatures that reveal the disk's temperature, composition, and velocity structure. Mass transfer rates typically range from 10 to the power of -11 to 10 to the power of -8 solar masses per year, depending on the system. This established baseline gives us a crucial advantage for SETI purposes. We know what natural accreting binaries should look like. Any significant deviations from these expected patterns could potentially indicate technological intervention. For instance, astronomers might detect anomalies, such as unexpectedly stable accretion rates or unusual periodic interruptions in mass transfer that don't align with orbital dynamics. Advanced civilizations could exploit these systems in several ways. The most straightforward approach would involve intercepting material in the accretion stream before it reaches the compact object. By positioning technological structures along the stream's path, a civilization could extract matter while allowing the natural gravitational dynamics to continue functioning. More sophisticated interventions might involve modulating the mass transfer rate. By manipulating the donor star's Roche lobe, the region within which material is gravitationally bound to the star, engineers could potentially increase or decrease the flow rate without disrupting the overall stability of the binary system. The accretion disk itself represents another potential target for exploitation. These disks contain material in various states of ionization, with temperatures reaching millions of degrees, ideal conditions for specific types of energy extraction. A civilization might tap into the disk's magnetic fields or utilize the temperature gradients to drive energy production, similar to our geothermal power plants, but on a vastly larger scale. Such interventions would create observable signatures. Current astronomical instruments could detect many relevant anomalies. Space-based observatories like NASA's TESS and the James Webb Space Telescope can capture precise light curves and spectral data, potentially revealing unusual patterns in brightness, temperature, or composition. Radio telescopes can detect unusual polarization patterns that might indicate artificial structures interacting with the accretion disk's magnetic fields. X-ray observatories like Chandra and XMM Newton can map the high-energy emissions from inner regions of accretion disks, potentially revealing unnatural gaps or structures. Several specific binary systems already display characteristics worth investigating. The cataclysmic variable star V Sagittae exhibits an unexpectedly accelerating period change that doesn't match theoretical models. Its orbital period is decreasing rapidly, and mass transfer is increasing at a rate that suggests the stars will merge around 2083, a remarkably short timescale, astronomically speaking. While natural explanations exist, the extreme parameters make this system a candidate for closer examination. KIC 846-2852, famously known as Tabby star, displays rapid, asymmetric dimming events that have defied conventional explanation. If part of a binary system, these dimming events could represent technological interference with mass transfer processes. Heartbeat stars like KOI 54 show unexpected resonances and energy distributions that some researchers suggest could indicate artificial manipulation of orbital dynamics to optimize energy extraction during close approaches. The case of SS Cygni presents another anomaly worth investigating. This dwarf nova system's outburst patterns suddenly changed in 2018, breaking a reliable 50-year record of predictable behavior. While natural explanations involving changes in the accretion disk structure exist, the timing and nature of this shift remain puzzling. For Stellavores civilizations, accreting binaries would represent energy sources and manufacturing centers. The diverse elements in stellar material provide raw materials for construction, while the extreme conditions in accretion disks could facilitate exotic manufacturing processes impossible in artificial environments. A civilization could position itself as a parasitic component of the binary system, extracting both energy and materials while allowing the natural dynamics to continue. The search for such techno-signatures requires a multidisciplinary approach. Astronomers must work alongside physicists, engineers, and complexity theorists to distinguish between natural phenomena and potential artificial interventions. Machine learning algorithms trained on thousands of known accreting binaries could help identify systems that deviate from expected patterns in subtle ways human observers might miss. Quantum signatures in gravity, fingerprints of intelligence. Beyond the visible light we observe from distant stars lies a deeper layer of reality where quantum mechanics and gravity intersect. In this mysterious domain, certain patterns of quantum coherence shouldn't naturally exist at large scales. Yet if we detected them, they could represent the ultimate techno-signature of an intelligence capable of engineering the fundamental forces of the universe. When we consider how advanced civilizations might manipulate their environment, we typically imagine massive structures like Dyson spheres or planetary engineering. However, a sufficiently advanced civilization might work at a far more fundamental level, directly manipulating the quantum substrate of space-time itself. This approach would be vastly more efficient than mechanical engineering, requiring profound mastery of quantum gravity principles that currently exist only in theoretical physics. The quantum nature of gravity remains one of physics' greatest unsolved puzzles. Think of it as a jigsaw puzzle with missing edge pieces. We have quantum mechanics describing subatomic particles brilliantly on one side, and general relativity explaining cosmic scale gravity on the other. But the border connecting them has eluded physicists for nearly a century. In this theoretical gap might lie the technological opportunities for advanced civilizations. Quantum effects naturally disappear rapidly in large systems. Quantum superpositions, where particles exist in multiple states simultaneously, are extraordinarily fragile, collapsing through environmental interaction in a process called decoherence. Imagine trying to maintain a perfect house of cards in a windstorm. This is similar to maintaining quantum states in the noisy universe. On astronomical scales, the universe's thermal background radiation alone provides enough disruption to eliminate quantum properties in open systems. This creates a potential signature, sustained quantum coherence across gravitational systems. Detecting gravitational waves exhibiting quantum properties over distances greater than theoretically possible naturally would suggest artificial intervention, like finding perfectly stacked cards in that windstorm. Such coherence might appear as non-random relationships between gravitational wave components that shouldn't naturally correlate. The gravitational field itself could potentially serve as a quantum information carrier. Oxford physicist Chiara Marletto has proposed experiments to detect whether gravity transmits quantum information between masses. If confirmed, advanced civilizations might exploit this property to create gravitational quantum networks using gravity rather than light for information transfer. These quantum gravity networks could enable communication across interstellar distances with significantly less power than electromagnetic signals. Unlike radio waves, which disperse with the square of distance, gravitational waves experience minimal weakening as they propagate through space. A civilization encoding quantum information in gravitational waves would possess an ideal method for maintaining coherent interstellar networks. Signatures of such artificial quantum gravity manipulation might include synchronized gravitational fluctuations across separated regions of space that maintain quantum correlations beyond what natural processes should allow. These would appear as persistent, phase-locked gravitational wave patterns that resist expected environmental degradation. Another potential signature involves quantum entanglement across gravitational fields. Entanglement creates correlations between particles regardless of separation distance. While naturally occurring entanglement between gravitational fields should be extremely rare over astronomical distances, artificially maintained entanglement could create distinctive patterns, like finding identical snowflakes falling simultaneously on different continents. The creation of artificial quantum vacuum states represents another potential technosignature. The quantum vacuum isn't truly empty, but filled with virtual particles continuously appearing and disappearing. Advanced civilizations might engineer regions where these quantum fluctuations follow non-random patterns, potentially for energy extraction or space-time manipulation. Natural quantum fluctuations follow random statistical patterns predicted by quantum field theory. Artificial quantum signatures would display organization, persistence, and non-random distribution, perhaps concentrating around specific astronomical objects or exhibiting periodic behavior defying thermodynamic expectations. In 2027, researchers at the Gravitational Wave Advanced Detector, a fictional future observatory, noticed something peculiar. Gravitational wave from a distant galaxy cluster showed quantum correlation patterns lasting thousands of times longer than theoretically possible. Initial skepticism gave way to excitement when the patterns were confirmed by 3 independent facilities. While natural explanations are still being explored, some physicists quietly acknowledge this could represent the first detection of technological manipulation of quantum gravity. Detecting such subtle quantum signatures represents an enormous challenge, but observational capabilities are advancing rapidly. Next-generation gravitational wave observatories, including the space-based LISA mission schedule for the 2030s and the proposed Einstein telescope, will significantly enhance our sensitivity to gravitational waves across wider frequency ranges. Quantum sensing technologies also offer promising detection capabilities. Quantum sensors can detect subtle gravitational field variations by measuring how these fields affect quantum systems. Arrays of such sensors could potentially detect coordinated quantum gravitational effects that classical instruments would miss entirely. Some researchers suggest we might already have data containing these quantum signatures. Certain gravitational wave events detected by LIGO show unexpected features that current models struggle to explain, highlighting the potential for discovering phenomena beyond our current understanding. If advanced civilizations are manipulating quantum gravity, the most likely locations would be near energetic astronomical objects like neutron stars, black holes, or galactic centers. These environments provide enormous energy densities that could power quantum gravitational engineering. The search for quantum signatures in gravity represents an entirely new paradigm in our quest to find extraterrestrial intelligence, looking not for biological life or conventional technology, but for engineering at reality's most fundamental level. This approach acknowledges that sufficiently advanced civilizations might transcend conventional technology instead directly manipulating the natural force or cosmic engineering. Dark energy constitutes approximately 68% of the universe's total energy content, yet remains one of the most profound mysteries in modern cosmology. This invisible force permeates all of space and drives the universe's accelerating expansion, a phenomenon confirmed in 1998 when astronomers observed distant supernovae appearing dimmer than expected, indicating they were further away than anticipated. Rather than slowing down due to gravity as scientists had predicted, the universe's expansion is speeding up. Dark energy behaves like a cosmic tide, flowing through the universe and seemingly violating our fundamental understanding of energy conservation. As the universe expands, more dark energy emerges, proportionally growing with space itself. This property has led physicists to describe it as the cosmological free lunch, an energy source that increases naturally with the expansion of space. The standard cosmological model treats dark energy as a constant property of empty space, assigning it a value known as the cosmological constant. This approach works mathematically, but offers little insight into dark energy's fundamental nature. Consequently, scientists have begun considering more radical explanations, including the possibility that what we observe might have technological origins. Consider this perspective shift. What if portions of the universe's expansion rate have been manipulated by intelligence operating at cosmic scales? The uniformity of dark energy distribution, appearing constant across vast cosmic distances, provides perfect camouflage for localized manipulation that might otherwise stand out against natural background processes. Advanced civilizations might approach dark energy as a fundamental resource to be harnessed. The vacuum energy density represents an immense potential energy reserve distributed throughout space like a universal reservoir. Even modest manipulation of this energy in limited regions could yield power that dwarfs conventional stellar resources. The vacuum energy density, at approximately 10 to the power of -9 joules per cubic meter, becomes formidable when integrated across cosmic volumes. A civilization capable of extracting just a fraction of this energy from a cubic light-year of space would access energy equivalent to millions of stars' lifetime outputs. Engineering at this scale would require technology operating at the quantum gravitational interface, precisely where our physics understanding breaks down. Such technology might manipulate vacuum energy through artificially induced phase transitions in quantum fields, creating regions where the effective cosmological constant differs from surrounding space. The energy requirements for such manipulation extend beyond the conventional Kardashev scale. While a Type 3 civilization harnesses the energy of an entire galaxy, approximately 10 to the power of 36 watts, vacuum energy manipulation would require energy control at the scale of 10 to the power of 52 watts, a hypothetical Type Omega civilization capable of accessing the fundamental fabric of reality itself. Detecting such engineering presents enormous challenges, but remains possible. Artificial manipulation would likely create subtle inconsistencies in the universe's expansion rate. Current cosmological surveys measure expansion by observing thousands of supernovae and mapping the cosmic microwave background. Focus analysis might reveal regional variations that don't fit natural models. Observational tests could include mapping expansion rates across different cosmic sectors to identify statistically significant deviations from uniformity. Natural variations should follow random distribution patterns, while engineered regions might show structured patterns or boundaries where expansion rates change more abruptly than natural processes would allow. Gravitational lensing surveys provide another detection avenue. Dark energy affects how light bends around massive objects, and artificial manipulations might create distinctive lensing patterns unexplained by conventional mass distributions. The upcoming Euclid Space Telescope and Vera-C Rubin Observatory will map gravitational lensing across unprecedented cosmic volumes, potentially revealing such anomalies. Spectroscopic redshift surveys measuring galaxy distribution at different distances could identify regions where expansion rates deviate from cosmic averages. The Dark Energy Spectroscopic Instrument, DESI, currently mapping the universe, will provide data precise enough to detect subtle variations previously invisible to observers. The Berkeley experiment searching for chameleon and symmetron particles connects to this hypothesis. These theoretical particles would mediate a fifth force varying with environmental conditions, potentially allowing control over how space expands in specific regions. If confirmed, such particles would provide both a natural explanation for dark energy and a mechanism for its technological manipulation. Advanced civilizations might generate chameleon particle concentrations to create regions where space-time expands at different rates, establishing energy harvesting systems, creating stable habitable regions, or enabling propulsion mechanisms that operate by manipulating expansion rates around spacecraft. Cosmic voids, vast regions containing few galaxies, present particularly intriguing targets. Some voids exhibit expansion rates differing slightly from theoretical predictions. Improved measurement precision might reveal structured patterns suggesting technological intervention. The filamentary structure of the cosmic web, with galaxies distributed along vast threads separated by voids, provides ideal conditions for hypothetical engineering projects. Civilizations might manipulate dark energy in voids to minimize disruption to existing galactic structures while maximizing access to vacuum energy. If such cosmic engineering exists, why haven't we detected definitive evidence? The answer lies in scale and perspective. From our limited vantage point, even massive engineering projects might appear indistinguishable from natural variations. Our cosmological models assume uniform physical laws, potentially causing us to interpret artificial manipulations as natural phenomena. Additionally, such engineering would likely occur in cosmic regions optimal for dark energy manipulation, potentially far from a Milky Way, in ancient galaxy clusters or cosmic voids, where intervention would cause minimal disruption to existing stellar systems. The search for non-uniform dark energy effects requires collaboration among cosmologists, quantum physicists, and SETI researchers. Traditional SETI focuses on electromagnetic signals that degrade over distance, while gravitational signatures propagate across billions of light years with minimal attenuation, potentially preserving evidence of ancient technological activity. Detecting megastructures through gravitational lensing. While electromagnetic signals fade across cosmic distances, gravitational footprints persist virtually unchanged, revealing the unmistakable geometric precision of engineered structures bending the fabric of reality itself. This fundamental property of gravity makes it our most promising tool for detecting large-scale artificial structures across interstellar distances. Gravitational lensing occurs when massive objects distort space-time, causing light from distant sources to bend around them. This phenomenon creates magnified, distorted, or multiple images of background objects. Astronomers have used this effect to discover exoplanets, measure galaxy cluster masses, and even map dark matter distributions. These same principles could reveal the presence of megastructures built by advanced civilizations. Natural objects like stars and galaxies produce gravitational lensing patterns with predictable symmetry. Spherical masses create circular Einstein rings, celestial halos of light, while elliptical galaxies produce elongated distortions. Artificial structures, however, would generate distinctly different signatures that break these natural symmetries in ways that tantalize astronomers searching for technosignatures. A Dyson sphere, a hypothetical megastructure completely encompassing a star to capture its energy output, would create a unique gravitational fingerprint. Unlike a solid sphere with uniform mass distribution, a Dyson swarm composed of countless individual satellites would generate a diffuse, granular lensing pattern with characteristic microfluctuations. These fluctuations would appear as high-frequency variations in a lensing strength that natural objects simply cannot produce. Stellar engines, theoretical megastructures designed to move entire star systems through space, would create asymmetric gravitational lensing patterns. The Shkadov thruster concept uses a partial reflector to direct stellar radiation, creating thrust on one side of a star. This asymmetry in energy distribution would produce a distinctive gravitational field gradient detectable through precision lensing observations. The time evolution of these patterns would reveal intentional stellar movement distinct from natural orbital mechanics. Perhaps most exotic are traversable wormholes, hypothetical tunnels connecting distant regions of space-time. If artificially stabilized by an advanced civilization, such structures would create distinctive negative mass, lensing effects where light rays diverge rather than converge. This anti-lensing signature would appear as a region where background objects appear systematically smaller and less distorted than surrounding areas, a pattern that violates our understanding of how natural mass distributions behave. Current observational capabilities are approaching the threshold needed for such detections. The Event Horizon Telescope, EHD, which produced the first black hole image in 2019, demonstrates our ability to resolve extremely distant objects with unprecedented detail. Its resolution of approximately 20 microarcseconds is equivalent to spotting a donut on the moon from Earth. This level of precision allows astronomers to detect subtle gravitational effects around massive objects. The James Webb Space Telescope, with its infrared capabilities, provides complementary data on thermal signatures that might accompany gravitational anomalies. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will vastly improve our gravitational lensing detection capabilities with its wide-field instrument surveying an area 100 times larger than Hubble. Ground-based observatories are evolving rapidly too. The Vera C. Rubin Observatory in Chile will conduct the Legacy Survey of Space and Time beginning in 2024. This decade-long project will image the entire available sky every few nights, creating a time-lapse movie of the universe that could reveal dynamic gravitational anomalies invisible in static observations. The real breakthrough may come from combining multiple detection methods. Simultaneous observations across different wavelengths can distinguish between natural phenomena and engineered structures. For example, a gravitational anomaly coincident with unexpected infrared emissions, unusual spectral lines, and periodic variations would present a compelling case for artificial origin. This multi-messenger approach leverages the strengths of different observational techniques while minimizing their individual weaknesses. Several candidate observations already warrant closer investigation. The star KIC 983 2227 exhibits unusual brightness variations with gravitational anomalies inconsistent with natural explanations. Assassin 15LH, classified as the brightest supernova ever observed, has gravitational lensing effects and energy output that have prompted some astronomers to propose artificial explanations. Perhaps most intriguing is Tabby's star. While its dimming events have received significant attention, less discussed are the subtle gravitational effects observed in surrounding dust distributions. These patterns show organization levels difficult to explain through natural processes alone. The combination of unusual light curves and gravitational anomalies makes this system a prime candidate for continued investigation. Looking forward, the Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will detect gravitational waves with unprecedented sensitivity. The proposed terrascope concept would use Earth's atmosphere as a giant lens, magnifying distant objects by a factor of approximately 45,000, potentially resolving features as small as a few kilometers on exoplanets in nearby star systems. Advances in computational methods are equally important. Machine learning algorithms can now identify subtle gravitational lensing patterns that human observers might miss, processing vast data sets to find statistical anomalies. Quantum computing will eventually allow real-time simulation of complex gravitational fields, making it easier to distinguish between natural and artificial origins. Conservative estimates suggest that within 15 to 20 years, Our combined observational capabilities will reach the threshold needed to detect kilometer-scale artificial structures within approximately 100 light-years of Earth. More optimistic projections suggest the first compelling evidence could emerge within this decade from existing datasets, not yet fully analyzed with the latest techniques. Throughout this journey, we've seen that the fundamental fabric of space-time itself may hold the key to detecting advanced extraterrestrial civilizations. While traditional SETI focuses on electromagnetic signals, gravitational signatures offer compelling advantages. They propagate virtually unchanged across cosmic distances and potentially reveal the most significant technological interventions. As our detection capabilities advance with instruments like LISA, the Einstein telescope, and quantum sensors, we're approaching a threshold that could change everything. The question isn't whether extraterrestrial intelligence exists, but whether we're finally developing the ability to recognize their cosmic fingerprints in space-time itself. Are we at last ready to end our cosmic isolation?